Beginning the session, we'll be discussing about after developing the backend system for an application, how to be scale them and all related with the stuff, right? So beginning the first slide, architecting for infinity, the mechanics of global backend scale. Now, the main component coming in this concept is server. You know very well that a server is a main component where all the data or even the local hosting and all lies upon, right? So what do you mean by scaling here? It is about handling increasing users, request, and data without crashing or slowing down. So the main purpose of the scaling is that in order to handle the increasing users, it might be the heavy traffic or even a low traffic coming to the website or application. We'll move ahead with the next slide. The starting point, you might have seen after developing a website on your local machine, you might register from your own site, which might be beginning with one or two users, and that could be handled very easily. But imagine once your website or application is deployed and it is going live in the internet and somebody is accessing, and in the same way, hundreds of people are trying to access the website, right? Then, uh, since there is a huge traffic coming to the website, it is difficult for the server, a single server, to handle it. And that's the concept we'll be discussing how to handle the traffic and all. You could see to the left side the digital baseline. The request goes to the single server, and from there, you'll also receive a response to the mobile again. For the backend, the server side engine handling APIs, databases, authentication, and logic. The main purpose of the server side is that it has to handle APIs, databases, authentication, and logic. Now, now comparing it with the real life. Suppose we take the physical analogy. There's a customer coming to the restaurant and he has ordered a food item, right? Then he'll be asking for the waiter, and the waiter or anyone has to reach out to the chef and has to prepare the food item, and then the chef goes into the pantry and prepares the food item and reaches you out again with the food item, right? So in that case, if the customers are in very low number, then the chef could be handling very easily. But what if there are many customers coming up to the restaurant and there are only one or two chefs in the restaurant? That is bit difficult. So a single chef handles the orders, cooks the food, and fetches the ingredients. At 10 users, this is quite easy. But as the number of customers begins, then the number of chef also has to be increasing in order to handle it. We'll move ahead. The breaking point. When 1 million users arrive, we have started with 10 users right now. But what if 1 million users arrive? These are the major issues faced while the traffic is increasing to the website or application. The first one is computer overload. CPU maxed out, memory usage explodes. Right. Compute overload in the sense the computation is over or is unbalanced. Right. So the CPU maxed out, memory usage explodes. The second factor is network saturation. Traffic explodes. Latency rises exponentially. So if the number of customers reaching out to the restaurant is increasing, but the chips are very low number, suppose one or two, then it might be difficult for chips to handle all the customers. Or even if they are trying to handle all of them, then they'll consume more time compared to having 10 or 15 chips compared to the having more number of customers. So in that case, it consumes more time. So that is what presented here. Traffic explodes and latency rises exponentially. The third component is, or the third factor is the data bottleneck. Database read or write logs slow everything down, right? And the next, the result. What might happen after facing all these consequences? The app crashes or the website crashes. Then users leave completely. So The single chef is handed 10,000 order tickets at once. The kitchen catches fire definitely. For a website, it might crash. And in a realistic way, the kitchen catches fire because the single chef is unable to handle all of them. We'll move ahead. The first fix. So what has to be done in order to resolve this problem? Suppose we have more number of customers coming to the restaurant, then we know the solution, and that the number of chefs has to be increased. But what in the case of computation or computer or laptop or in the case of a website, how is it resolved? The solution is upgrading or multiplying, both of them. But let's find the most efficient one: upgrading versus multiplying. Now, under upgrading, the approach is vertical scaling, and under multiplying, it is horizontal scaling. The mechanism is we can add RAM, better CPU, faster SSD to one machine. But in the case of multiplying, horizontal scaling, we can add more servers to the network so that servers handle each other or the data or the requests coming up. Right. The advantages in the upgrading architecture are very simple, quite easy, quite comfortable. Whereas in the case of multiplying, it can handle a lot of scalable users, or it can handle scalability very easily in a large number, and it can tolerate easily fault tolerance. And coming to the disadvantages, in the upgrading, it is expensive and strict hardware limits exist. But in the case of multiplying, requires complex network management. And coming to the failure risk or flaws, it's a single point of failure. That is, if the server dies, the application entirely dies. But coming to the multiplying, that is redundant. Redundant in the sense having many copies or duplicates. So having multiple servers here, if even a single server dies, traffic reroutes to the next server which is available. Right. And coming to the industry standard, they are legacy systems. And coming to the case of multiplying, they are cloud native applications. I mean, they could be handled through cloud native applications. We'll move ahead. Distributing the load, traffic cops, and state lessons. Imagine there are many number of the ones traveling out on the Sunday, and there's huge amount of traffic. And at a point, the Chaurasta or whatever we say, the intersection of four roads, there, what if the traffic increases a lot, right? Then there has to be some traffic cop over there who shall be managing the traffic, like people, like letting one side of the road to be allowed and letting the other roads to be occupied to wait some time. In that way, we have something called load balancer in the computation side, which handles same like a traffic cop, which could be called NGINX, HA proxy, AWS, ELB, and all those which handle um, those which work like a traffic cop in the computation side. They distribute traffic, prevents overload, and runs health checks. There is also a component involved in this, that is stateless servers. Servers cannot permanently store user session data locally. Any request can go to any server. Session data is moved to a central fast cache. Now, in the cache, in the sense, it's a RAM where the data would be stored and which is very much easy to be retrieved. Right. We'll move ahead. The speed layer, intercepting the database bottleneck. Right. The problem what we face: repeated database queries are expensive and slow. Imagine you have ChatGPT in your case, or you're utilizing the ChatGPT, and if you're giving the input continuously, then there is always the API limit expiry, or what we call the API limit to be exceeding always the number of times the give the input or provide the input. Right. So if the query is the same, repeated, then the API limit exceeds, and the computation cost also turns much more expensive. Right. So the solution for this: store frequently used data in in-memory caches, which is way better. Right. You can store the repetitive data at a place, and you can try to retrieve that rather than uh, repeating the queries again and again and fetching the data again and again from somewhere and somehow randomly. The result: millisecond responses and drastically reduced database load. Right. It reduces the database load and provides a response within milliseconds. We'll move ahead. Scaling state, splitting reads and writes. Right. Suppose there is a user providing an input. The input might be for fetching the data, or else the input might be in order to add the data. Right. So there, if he is willing to fetch the data, then it is somewhat called as read operation. If he is trying to add the data, then it is somewhat called as write operation. Right. You can also find in a message. Right. Primary DB handles all state changes, read replicas, synchronize with the memory, handle read heavy traffic. And what are the benefits? Faster reads across the system, built-in fault tolerance. If a replica dies, another takes over. Right. Having multiple copies, even if one of them is failing to function, then another would be taken up, which is already available in that way. We'll move ahead. Sharding, shuttering the monolith database. Now, what is the mechanism here? Splitting large databases into smaller, independent pieces based on a shard key. Now, you might have a doubt. What is sharding here? Sharding is nothing but splitting into multiple parts, or it could also be called type of partitioning. Right. Now, what is the benefit? We achieve parallel processing and massive, near infinite scalability. Then, the trade off: extremely complex queries, joining data across shard 1 and shard 2 becomes a massive engineering headache. Right? We'll move ahead. The complexity crisis, transitioning to microservices. Now, what might be the issue? What might be the flaw? What might be the complexity, difficulty, trouble that might be faced? The monolith and compared with the microservices. The API gateway, the unified front door for authentication, security, and logging. The microservice architecture, splitting the backend into smaller, specialized services. Now, why do we need? Why do we follow this and all? Because independent scaling, you can find independent scaling, faster deployments, and easier maintenance. You can also follow the images shared here in order to understand in a much more easier way. Right, we'll move ahead. Asynchronous scaling, queues, and background workers. Now, try to understand what does it mean by asynchronous and synchronous before getting into the concept. Right now, suppose you're standing in a line and you will have to wait for the people standing before you or in front of you to move ahead. I mean, to move aside, and then you can follow the line and you will be moving forward. Right. So the methodology or the way of waiting for someone in order to clear the path and in order to let you move ahead or move you forward, that is all describing synchronous. And asynchronous in the sense, uh, people do not stand in a line, rather they can move parallelly. Right. That is all about asynchronous. You can also follow the picture mentioned here or shared here. Right. It goes from the user to the server and to the heavy video processing to the database. But in asynchronous, it goes to the user to the server, or it might also return back to the user, right? And from the server to the message queue, and from there, background worker AI inference. So the entire pipe is logged and logged in a synchronous. But workers pull tasks from the queue and process heavy jobs in isolation. That is in the case of asynchronous. Now, what is the takeaway? Never block the user for slow tasks, emails, processing, notifications. Because if you try to wait, or if you let the users wait for some more time, then there it leads to delay and latency. We'll move ahead. Defeat in the speed of light. Content delivery networks. So, what exactly do we mean by content delivery networks? They are the one which are actually working on the global edge in order to share the data in a global level, and that too throughout the internet. Right there, the CDNs are playing a main role. You can find the goal written here: serve statistic content, images, video, CSS physically closer to the user to reduce geographic latency. Now, what is the result? You find drastically reduced backend network traffic and near instant asset loading globally. Right? You can find the data wherever you need throughout the internet through CDN. That is content delivery networks. Right? They may include Cloudflare, AWS, and anything else. We'll move ahead. The automated connector, containers, and Kubernetes. Now, why do we have to talk about containers and Kubernetes? Right. Suppose you have worked on a project so far and you want to store it somewhere, as well you wanted to share it somewhere else. Now try to imagine you have downloaded all the modules required for the project, and you want to share the entire project including the modules to the some other person or your co-employee working with you. Right. Then in that case, if you are trying to share the project as it is, but you see that some modules are not present after being shared. In that case, the containers in Kubernetes are playing a main role so that you can even store the modules directly and share them directly to the co-employee or whomever you're working with. So the containers you might find here, they are lightweight, portable, isolated environments, packaging the app and its dependencies. Coming to Kubernetes, that is K8s, the brain manages deployment, scaling, network routing, and auto recovery of containers. Coming to auto scaling, elastic infrastructure that matches cost and capacity directly to user demand. You can also try to understand through the image displayed here. Yeah, we'll move ahead. The master blueprint, anatomy of an Instagram upload. Right. We will go through an example and try to understand in a final part. Right. The first one, upload hits CDN. Suppose you are trying to upload a post or some reel or anything else. Immediately, if you click on the upload, it hits the CDN first, routed to load balancer. Then API gateway authenticates via microservice, and then payload saved to storage, metadata to database, and then Redis cache updated with new feed data, and then event queued for background workers, and the last process image pushed to the CDMs globally. And all of this happens within 2.5 seconds, which is quite impressive that it happens all within seconds, and you see all the data wherever you want, easily accessible. Right. You might also find the flowchart here presented. Yeah, we'll move ahead. Survive in the chaos, security, faults, elements. No matter which operation or which project we are dealing, there are definitely some flaws, faults, or security issues faced. Right. So we'll try to understand how to resolve them or how far we can try to reduce them. The observability dashboard, CPU usage, and latency spikes, the error rates. Without constant monitoring, that is, without constantly observing Datadog or Prometheus, which can be used, failures in distributed systems go unnoticed. Right? It's true that without observing what is happening within the project. Failures cannot be noticed. Then, the defensive mechanisms. The first one, rate limiting. An impenetrable shield blocking malicious bots and DDoS. Example, strictly 100 requests per minute. Right. And then the circuit breakers. A mechanical switch, stopping traffic to a failing microservice, preventing cascading system failure. Rule of scale, servers fail constantly. Scalable systems don't prevent failure, they engineer around it. That is, utilizing all of them, scalable systems do not face any failure and they can be engineered. Right. We'll move ahead. The next frontier and the evolution complete. AI and the new scaling paradigms. You can see modern scale now includes AI, or you can also relate it with the real world where you'll find the new AI era coming up, right? So model scale now includes AI, recommendations, fraud, chatbots, and all. Introduces new bottlenecks requiring massive GPU clusters, vector databases, and complex model caching. So we'll also get into the 60-second recap, that is compute. We scaled out horizontally and balanced the load. And then we cache aggressively, replicated, and shared the state for the data. Then we split into microservices, queued heavy tasks, and automated with Kubernetes. So it goes from a single chef to a global automated franchise. We have architected for infinity so that any amount of data could be shared globally and could be accessed anywhere, anyhow.